Greetings and salutations. In this screencast, we take a look at volumes of solids of revolution. So I should probably explain what I mean by a solid of revolution. So we're just going to imagine that we have some function, maybe it looks like this, some function f of x on some interval from a to b. And what I want to do is I want to take the area that's under f from a to b, and I want to revolve it 360 degrees about the x-axis. I want to revolve it a complete revolution. It's got to come out of the paper, down like so, through the paper, into the anti-paper, and back again. So I get a three-dimensional, oh, here, it'll be easier if I make the picture look a little better. Let's get rid of this, and let's replace it with something that's a little more obvious. There. If I take this and I spin it around 360 degrees, what do I get? Well, let's clone this, bring it over here, and consider what happens in 3 dimensions. So I come out here, and I'm going to clone this again, and flip it upside down and bring it like so. If I take this region and spin it around 360 degrees about the x-axis, what I end up with, oh, hello, what I end up with looks oddly like a vase or a vase if you're from a different part of our state. I get this 3-dimensional figure. It's a vase. And the question is, what is the volume of the vase? And you're thinking, well, I don't know that. But I know that in the past, what has worked for us is we take this region and we approximate it with rectangles. And we spin those rectangles around, and we see what happens when we spin those rectangles around. Well, what happens if we spin those rectangles around? If we spin those rectangles around, what do we end up with? Tuna cans. This rectangle, if you spin it 360 degrees, becomes a tuna can. So I have to ask myself, what is the volume of a tuna can? Well, a tuna can is just a fancy name for a cylinder, and the formula for the volume of a cylinder is pi times the radius squared times the height. Well, the height of the tuna can is a very teeny tiny change in x, and pi is pi. So the question is, what is the radius of the tuna can? What is the vertical distance from the center to the outside? And if I were to take this and bring it over here, I would find that is a function value. It's this function value. This is a function value. And so this is the volume of one tuna can. I'm going to make a whole bunch of tuna cans, make them really, really thin, jam as many of them as I can in there, and I'm going to get that volume is pi times the integral of my function squared dx, delta x becomes dx, from a to b. This is the generic idea, well, it's the general idea behind volumes of solids of revolution. Pi times a radius squared integrated over a closed interval. This is the big idea. So if you have this, you have everything you need to do the examples that we're about to do. Like this one. Let's take the square root curve on the interval from 0 to 4, and let's spin that 360 degrees about the x-axis. And if we spin that 360 degrees, this region right here, we spin this region 360 degrees about the x-axis, you end up with something that looks like a bullet. Maybe it's a bullet? and I want to know the volume of the bullet. And the volume of the bullet is an integral. It's an integral of pi times the radius squared times the thickness of a tuna can. Because I'm going to take this thing and I'm going to spin it around, and the radius of the tuna can, is going to be the same as this function height from 0 to 4. Now I can do that. I mean, if I've got a calculator, I can just fit into that, but I can actually do this without needing the machine. Square root of x squared is easy. And then I know how to take an antiderivative. And so 16 minus 0, take half of it, multiply by pi, and I've got a volume. Now these problems become slightly more difficult for us because I don't really know if this is a reasonable answer to this volume problem. That's harder for me to see, whether or not I have a reasonable answer. But certainly the calculus is solid. Pi times an integral of a radius squared times a thickness. Okay, let's get a little triggy with it. We'll get a little triggy with it. This is secant x. And it's secant x from 0 to pi over 3. This is the region in question, and I want to revolve it about the x-axis. So again, we approximate with a rectangle. We spin that rectangle around. We get a tuna can, and the volume of a tuna can is pi times radius squared times the thickness from 0 to pi over 3. What is the radius of the tuna can? It's this height, right? So I ask myself, what is the function whose derivative is secant squared of x? Oh, I hope the other class has the trig heavy final exam. Oh man. And then I got to know what the tangent of pi over 3 is. Well, why don't you just ask me to build a radio out of bamboo and coconuts? Yeah. Okay? Pi radical 3. Okay? Again, it's pi times an integral of the radius squared times the thickness, where that thickness is usually a dx. Okay, so you might well wonder, how can I make this difficult? Well, I can't really make it difficult, but I can make it just a scotch complicated. Let's let R be the region between y equals radical x and y equals x. That would be from 0 to 1. If I need to show you that, we're in trouble. I want to take that region R, and I want to revolve it 360 degrees about the x-axis. So if I do that, I sort of imagine this three-dimensional solid, and here's the outside edge. Oh, no. Here's the inside edge. Here's the outside edge. Okay, that's my region. So I've got this thing spinning around. The problem is, when I do my rectangle, and I spin the rectangle around the axis, I don't get a tuna can. I get a washer. I get a tuna can with a tuna can sized hole in the middle. And so the thought occurs to me that if I found the volume of this tuna can and the volume of this tuna can, and subtracted them, I'd have what I'm looking for. If I did this tuna can, right, pi times radius squared, and then I did this tuna can, pi times that radius squared, and subtracted the answers, I would have what I was looking for. Now we can combine these together into one integral so that we're not doing too much work, because both of these are pi times an integral from 0 to 1 of what? Of this minus this. So the general principle when we're dealing with what are called washers, this is the washer method, the general principle is that we do pi times an integral from a to b of a big radius squared minus a little radius squared dx, where big R is this big radius and little r is this small radius. So from here it's not that bad. From here we're just doing an integral from 0 to 1 of x minus x squared, and I'll leave it up to you to prove that that's pi over 6. I'm just interested in making sure you know how to set this thing up. So when there's a hole in your solid, dear Liza, you're doing the washer method, and the washer method is pi times an integral of big radius squared minus little radius squared. Okay? So let's go one more. Let's suppose that our region is the region bounded by y equals x and y equals x squared, and again that's from 0 to 1. This is my region. And let's suppose that instead of spinning it about the x-axis, we spin it about y equals negative 1. We're spinning around that line. Again, when we spin it around, we're going to get some crazy three-dimensional solid. Oh, whoa, yes, hello. We're going to spin it around this crazy solid like this. And I'm thinking washers, because I'm pretty sure there's going to be a hole in the middle of the solid. And so I'm pretty sure that I'm supposed to do pi times an integral, probably from 0 to 1, of somebody squared minus somebody squared dx. And the questions are twofold. What is the big radius? This would be the big radius. And what is the small radius? This would be the small radius. So the big radius runs from x down to negative 1. So this much is x, and this much is 1. Together, they're x plus 1. It's this function value plus another 1. Similarly here, this much is x squared. This much is 1. So together, x squared plus 1. And I can leave it up to you to expand the brackets, take the antiderivative term by term. I don't have to show you that that's 7 pi over 15. I have to show you how to set that up. All right, so I will give you one more that we'll walk through together. The region in question this time, this is 2 minus cosine x, and this is cosine x. The region will be this region, and we're going to revolve about y equals 3. We're going to revolve about the line y equals 3. And I'm pretty sure that if I take this region and I spin it around, I'm going to get some three-dimensional solid with a hole in it. And if I've got a hole in it, then I've got to go whoa, I don't even know what that is. I'm pretty sure I've got to go washers. And washers is pi times an integral from 0 to pi over 2 of somebody squared minus somebody squared dx. Two questions. The first question is, what is the big radius? And the second question is, what is the small radius? The big radius goes from the curve to from the center to the curve on the outside. This is going to generate the outside edge because it's further away from our line. The other is the radius from the center to the inside curve. This is generating the hole. This is what's making your hole. So this thing, well, what is that? Well, this whole distance is 3, and this is cosine x. This whole thing is 3, and this is 2 minus cosine x. And I don't even feel like doing all that by hand, and even if I could, I need a double angle substitution, and so I'm just going to finint that and round to 3 decimal places as advertised. So when you come to class on Friday, we have to know, well, it could be Friday. You could be looking at this at some future year where the schedule changes. When we come to class next time, you're going to want to know how to revolve around axes. I'll see you then.